Most important point about A star are two. One is that if there is a path from S, the start node to the goal node, optimal path, then the optimal path, some node from the optimal path is always there on the open list. And the optimal path to that node has already been found. Okay, so such a node always exists on the open list. The optimal path to that node is already found, and all the ancestors of that node are in the closed list, and that node is in the optimal path. This is the most important point about A-star algorithm. And we have proved that A-star algorithm halts using this property, and the fact that H is less than or equal to H star always. A star also finds out the optimal path. And then if any node F, if any node N has F value strictly less than F star S, then before termination, that node will be expanded by A star, which is why less informed heuristics give rise to lots of useless expansions. And if A star does not expand a node N before termination, then by implication, F value of that node must be greater than or equal to F star S. F star S is the cost of the optimal path from start node to the goal node. So these observations are important, and 3 and 4 imply that a better heuristic performs better. Okay, if a heuristic is closer to the actual cost of reaching the goal node for any node, then this heuristic is better. And we have seen that if H2n is greater than H1n for all node n, then the less informed heuristic, less informed A star 1 will be expanding at least all the nodes of A star 2. Okay, this has to happen. So these are the things which you need to verify in the lab. And on Thursday, when you have the lab vivas, these are the things which we will look for. An important point I have to tell you for the lab is that you have to implement exactly what is asked, okay, in the class. The lab exercise will shadow the theory being covered in the class. Okay, so the theory which is covered in the class, the conceptual foundations have to be verified in the lab. Okay, it is impossible that you will be understanding all the nuances of A star without implementing A star in practice and seeing its operations on actual problems. Now, we also have been in parallel looking at lots of foundational ideas, charge Turing hypothesis, physical symbol system hypothesis, uncomputability, NP completeness and NP hardness. AI as a discipline is multidisciplinary. Difference between brain computation and Turing machine, this we started. So these are the main points covered in the last week. If you have any question or comment, you feel free to make them or ask them. Okay. So in the lab, one of the non-trivial tasks is to maintain the open list and closed list. Management of these two data structures is important. Okay. Now we come to a very important property which is imposed upon as a constraint on the heuristics. Okay, so we're almost finishing A star and then moving on to another pillar from the other side of other paradigm of artificial intelligence, which is connectionist AI, neural network based AI. So, okay, so we'll juggle between symbolic AI and neural network based AI because deep learning is the paradigm for AI today. So if you have carefully read the general graph search algorithm, there is this step number 7, which asks you to establish a parent pointer. And if a node has been generated again, okay, and is in the open list, then you have to examine if the parent pointer needs to be revised, okay, with respect to the new expansion. That is to always maintain the least cost path from the start node to that particular node. Okay, this is the very specific point which separates Dijkstra from breadth first search. Okay, breadth first search did not give you the optimal path, mainly because of this point. Breadth first search says that the GN value is equal to the number of arcs from S to that node. Dijkstra's algorithm says GN is equal to the sum of the costs of the arcs from S to that particular node. Okay, so while Dijkstra maintains the least cost path at every stage, breadth first search need not. It only maintains the least distance path in terms of the number of arcs. Okay. So here we are required to change the parent pointer of a node in the open list if it appears once again. But in the closed list, we have to do much more work. In the closed list, we have to see the children, the grandchildren, and change their parent pointers, which is a very costly operation. Okay, and it turns out that with a very simple and intuitive heuristic, very reasonable also, we need not visit the closed list again. Okay, so here is an example. You can look at the slides for the details. So this is the status of search for this graph. All the green nodes are in the closed list. Okay, and the nodes with yellow border are in the open list. The upward arrows are parent pointers. Okay, so this is the state of affairs. And now, in the next stage, the parent pointer changes from 2 to 3, which was here, okay, 2 to 3, to 2 to 1, okay, through an expansion, okay, 2 to 1. And then this parent pointer redirection needs to be percolated for 4 also. Okay, it changes from 4 to 6 to 4 to 2. Okay, because a less costly path has been found. Okay, so this is this is a case. This example is from Principles of AI. Niels J. Nielsen, from which I'm mostly covering the material. So this kind of percolation of parent pointer redirection will happen for closed list nodes also. So once you look at the slide, you will be able to see, you can see the textbook also. There is another graph where again, you can verify that the node 3, this violates what is called the monotone restriction, and it will require parent pointer redirection percolation, okay, when we move forward. So let's define monotonicity, which is a very reasonable definition. A heuristic HP is said to satisfy the monotone restriction if for all P, every P in the graph, HP is less than or equal to HPC plus cost of P comma PC. So this is really triangular inequality. Okay, so the distance from P to the goal node, direct distance from P to the goal node, is less than or equal to distance from P to its child PC and the distance of the child to the goal node. Okay, this is nothing but triangular inequality. And we say that this heuristic is satisfying the monotone restriction. Okay, so we'll ground it very soon to see actual heuristics which satisfy monotone restriction. The theorem will come to. Let's look at grounding of the monotone restriction. So let's say we have this configuration, okay, the start configuration 7, 3, 1, 2, 4, 8, 5, 6, and the goal node is 1, 2, 3, 4, 5, 6, 7, 8. with the blank at the rightmost lower corner. So from this configuration, okay, we move to the configuration below, where 4 has moved up into the blank space. Okay, so let's think about the display style heuristics. Hn is the number of display styles. Now, is Hn monotone? You see, n here, Hn is 8. How many tiles are displaced from their position? 1 is displaced, 2 is displaced, 3 is displaced. Every tile is displaced from its position. So the value of H is 8 at this configuration. At at n dash, so 4 has moved to this position, but nothing has really improved. Okay, nothing has improved. All the tiles are displaced from their position. So Hn dashed is also equal to 8. And the cost of moving from the upper configuration to lower configuration is 1. Okay, so clearly Hn is less than or equal to Hn dashed plus C and n dashed. Okay, now what is the argument? If a tile, okay, if the movement of a tile does not change the number of displaced tiles, then surely the triangular inequality is satisfied, right? Because you have incurred the cost of moving from one configuration to another. And if the movement of the tile decreases the number of displaced tiles, then you have reduced H by 1, but you have incurred a cost of 1. Okay, so they cancel each other. And again, therefore, triangular inequality is satisfied. Hn is less than or equal to Hn dashed plus C. Clear? So display style heuristics is satisfying monotone restriction, satisfying triangular inequality. What can we say about the Manhattan distance heuristic? Manhattan distance heuristic, is this also satisfying triangular inequality? Why so? What is the argument? So you're saying it is not satisfying? So Manhattan heuristic will not satisfy triangular inequality always? Oh, sure. So let's see. Any move can either increase the H value or decrease it by at most 1. Either increase the H value or decrease it by at most 1. Cost is again 1. Hence, the heuristic also satisfies the monotone restriction. Right? So Hn less than or equal to Hn dash plus C. So Hn dashed is either 1 more than Hn or 1 less than Hn. Okay? And therefore, and cost is always 1. And therefore, Hn must be less than or equal to Hn dash plus C. It does satisfy. Okay. So monotone restriction also satisfies the triangular inequality. And Manhattan distance also satisfies triangular inequality. So both the heuristics satisfy triangular inequality. Okay. And this means that you do not have to go to the closed list and change the parent pointer, which again you should verify, okay, by observing the G values of the nodes in the closed list. Okay, now let's go to the theorem. If monotone restriction, which is also called triangular inequality, is satisfied, then for nodes in the closed list, redirection of parent pointer is not necessary. In other words, if any node n is chosen for expansion from the open list, then Gn equal to G star n, where Gn is the cost of the path from the start node S to n at that point of the search when n is chosen, and G star n is the cost of the optimal path from S to n. Okay, so this is very remarkable. You choose any node for expansion, send it to the closed list. The G value for that node must be equal to G star. Okay, so this is the least cost path from S to that particular node N. It has to be because of the monotone restriction. And the proof follows. Okay, so this is the theorem, and we'll prove the theorem. Now, there's an interesting relationship between monotonicity and admissibility. Okay, if a heuristic satisfies monotone restriction, then that heuristic must be admissible. Okay, but the opposite is not true. So if a heuristic satisfies monotone restriction, H value must be less than or equal to H star. The algorithm automatically becomes A star algorithm. Okay, so the statement is the following. If Hni is less than or equal to Hni plus Cni for all ij, then Hni is less than or equal to H star Ni for all I. Okay, this is quite remarkable. If a heuristic satisfies monotone restriction, it must be admissible. Let's see the proof. Would you like to attempt a proof? Any idea as to how to go about proving it? Okay, it is this way. So in most of the proofs involving A star, you have to start from observing the optimal path. Okay, you start from the optimal path from S to G, or from any node to G. The optimal path from any node to G. Let us consider the following as the optimal path starting with a node N. Okay, we are interested in showing that Hn is less than or equal to H star N. That is our goal. So N is N1, N2, N3, Nm equal to Gi. So we are considering the path, optimal path from N to the goal node G. Okay. So we observe that H star N, that is the cost of the optimal path from N to G, must be equal to Cn1 N2 plus Cn2 N3 plus and so on, Cm minus 1 up to Cm minus 1 Gi. This must be H star. Okay. So since the path given above is the optimal path from N to Gi. Now, Hn1 is less than or equal to Hn2 plus C1N2 is equation 1. This is because of monotone restriction. Cn1 must be less than or equal, Hn1 must be less than or equal to Hn2 plus Cn1N2. Hn2 must be less than or equal to Hn3 plus Cn1N2 Cn2N3. Finally, Hm minus 1, okay, should be less than or equal to Hgi plus Cnm minus 1 Gi. So this is the picture. Okay, this is the picture. You are considering an optimal path from N to G. So all these inequalities are satisfied starting from N. Okay, and now if we add all the left-hand side elements and the right-hand side elements, then we have these cancellations. Okay, Hn2 cancels with Hn2, Hn3 cancels with Hn3. Okay, then Hm minus 1 cancels with Hm minus 1, and okay. So Hn2 cancels with Hn2, Hn3 cancels with Hn3, and so on. And then we get Hn1, which is Hn, less than or equal to Hgi plus all these costs. Okay, and Hgi by definition is 0. So we have now Hn is less than or equal to the cost of all the arcs leading up to G. And the sum of these costs is equal to H star. Okay, so this is a very, very elegant observation. Just set up the inequalities and see that there are cancellations from left-hand side and right-hand side. and the H value is proven to be less than or equal to H star. Okay. So if a heuristic satisfies monotone restriction or triangular inequality, it must be admissible. Okay. A very powerful observation. And the ask is very reasonable. A very intuitive ask. So display styles heuristics and Manhattan distance heuristics, both of them must be admissible from this point of view also. Okay, they are already proven to be less than or equal to H star before. But the opposite is not true. Okay, a heuristic may satisfy admissibility, H less than H star everywhere, but it need not be monotonic, need not satisfy monotone restriction. So here is the counter example. We have H star N1 equal to 3. Okay. H star N2 equal to 2, H star N3 equal to 1, and so on. Hn1 is 2.5, Hn2 is 1.2, Hn3 is 0.5. The cost of each arc is 1, and HGI is equal to 0. H is less than or equal to H star everywhere, but monotone restriction is not satisfied. Where is it not satisfied? So it is not satisfied for Hn1. No. Hn1 is 2.5, Hn2 is 1.2, and cost is 1. 2.5 is not less than 2.2. Okay, so MR implies admissibility, but not vice versa. Okay, now a sketch of the proof that monotone restriction leads to optimal path for every expanded node. You don't have to redirect a parent pointer. Okay, again, these proofs are better done on the board slowly, but these lectures are being recorded, so I'll read from the slides, and the proof is quite lucidly given. Okay, it is expanded over the proof given in the book by Nielsen. Go through the proof. So again, we start with the optimal path. Let S n1, n2 up to nm, nk be an optimal path from S to nk, all of which might or might not have been explored. Okay. Let nm be the last node on this path, which is on the open list. That is, all the ancestors from S up to nm minus 1 are in the closed list. Okay. So for every node np on the optimal path, we know that G star np plus Hn np, Hnp is less than or equal to G star np plus C np np plus 1 and H np plus 1. That is due to monotone restriction. Okay. Then G star np plus Hnp is less than or equal to G star np plus 1 plus Hnp plus 1 on the optimal path. And G star nm plus Hnm is less than or equal to G star nk plus Hnk by transitivity. So, this is one relation which will hold on the optimal path if monotone restriction is satisfied. Okay, that G star plus H value. Okay, G star plus H value is less than or equal to the G star plus H value throughout the optimal path. Okay. Now, since all the ancestors of nm in the optimal path are in the closed list, Gnm is equal to G star nm. Okay, that is by observation. This implies that Fnm, which is equal to Gnm plus Hnm, is equal to G star nm plus Hnm, which is less than or equal to G star nk plus Hnk. This is because of the previous observation, which is by transitivity. Okay. Now, if nk is chosen in preference to nm, okay, then fnk must be less than or equal to fnm. This is the property of the A-star algorithm. That means gnk plus hnk must be less than or equal to gnm plus hnm. And GNM is G star NM because all its ancestors have gone in the optimal path are in the closed list, which is equal to G star NM plus HNM. And this is less than or equal to G star NK plus HNK. Okay. So GNK is less than or equal to G star NK, but GNK is greater than or equal to G star NK by definition. Okay. No path length can be uh, uh, less than the cost of the optimal path. Hence, GNK is equal to G star NK. This means that if NK is chosen for expansion, the optimal path to this from S has already been found. Okay. The key point here is that if MR is satisfied, nodes in an optimal path have to get expanded in the order of their distance from the start node. Okay. And try proving this by induction on the length of the optimal path. Yeah. Okay. So, uh, this NP is a node on the optimal path. Okay. Then consider the child of NP, which will be NP plus 1. So G star NP plus HNP is the quantity being considered. This must be less than or equal to G star NP plus C NP NP plus 1 plus HNP plus 1, monotone restriction. Now G star NP plus HNP, C NP NP plus 1 plus HNP plus 1 must be equal to HNP plus, sorry, G star NP plus C NP plus 1 must be G star NP plus 1. Okay. And then by transitivity, G star NM plus HNM must be less than or equal to G star NK plus HNK. Transitivity. So this applies for every parent child. Okay, this quantity G star plus H is less than or equal to for every parent child. Okay, and therefore, okay. So this was the proof. Okay, go through the slides, and if necessary, we can come back to it. Now, monotonicity of F-values. F-values of the nodes expanded by A star increase monotonically if H is monotone. So if monotone restriction constraint is satisfied by the heuristic, then the F-values are non-decreasing. Okay, F-values of the nodes which are expanded are non-decreasing. These also you should verify in the lab. I'll send you all the statements which you should verify in the lab. If the monotone restriction is satisfied, the F-values of the nodes expanded have to be non-decreasing. They increase monotonically. Okay, the F-value of any node expanded must be equal to its previous expanded node or greater than the F-value of the previously expanded node. Okay, so all these are very intriguing properties, but following logically from the properties given. For this again, the proof is given. Okay, and a better way to understand the monotonicity of F, N1, N2, F3, Nk be the F values of the K expanded nodes. The relationship between two consecutive expansions, Fni and Fni plus 1 nodes always remain the same. That is, Fni is less than or equal to Ni I plus 1. Okay. Okay, there are quite a few observations about monotonicity of F. But the main point being covered about monotonicity today is that monotonicity leads to admissibility. Whenever monotone restriction is satisfied, a node picked up for expansion has already found the optimal path. The F values of the nodes expanded are non-decreasing. These are the consequences of monotone restriction. Okay, we'll come to these details gradually again. So let me move to this point that a list of AI search algorithms, A star is most famous. Then AO star and IDA star, which is iterative depending, they're special cases of A star. Then minimax search on game trees is again a search algorithm. Viterbi search on probabilistic finite state automaton is a famous search algorithm. Hill climbing, simulated annealing, gradient descent, stack-based search, genetic algorithms, mimetic algorithms. All these are AI search algorithms, okay? And they have been extensively explored in the 1980s and 90s with umpteen number of papers coming for these AI search algorithms. But all of them are based on some variation of A star, except Viterbi, which will also be covered in the class after some time. Okay, so now let me move to some foundational points and go to connectionist AI, which is another paradigm of AI. We will do a more leisurely discussion on monotone restriction, okay, with lots of fine points for them. But I'd request you to go through the slides, okay, which very elaborately discuss all these fine points. So we have discussed some foundational points, and we said that symbolic AI is based on symbol manipulation, that is Turing machines. Turing machines have infinite tape and a finite state automation, which you have seen before. And von Neumann machine has symbol transfer between CPU and memory. Now, the challenges to symbolic AI came from the following observations: that a large number of computations and information processing tasks that living beings are comfortable with are not performed well by computers. Okay, this was the observation when neural computation was gradually becoming more and more assertive. So what is the difference between symbolic AI and connectionist AI? The difference is are the following. Brain computation in living beings are very good at pattern recognition, whereas Turing machine-based computation is very good in numerical processing. Okay. In brain computation, the computation is learning oriented. In Turing machine, it is programming oriented. A human being has to sit down and give the transition functions of the Turing machine to define the computation. In brain, it is distributed and parallel processing. In Turing machine-based computation, the computation is centralized and serial. Okay, it is step by step, one step after another, and the CPU is the central processing unit which does the computation. The memory is content addressable. We get a part of the information and the rest of the information is retrieved. Whereas in Turing machine, it is location addressable. It is better understood by von Neumann machine. The CPU places an address on the address bus, and the content from that location comes to the CPU for further processing. Okay, so these are important differences. Now, we have seen that many things that living beings are comfortable with are not performed well by computers is not true anymore. Okay, because for example, we are seeing that deep learning systems are excellent in language processing, scene understanding, classification, and so on. Okay, which were not the case some 30, 40 years back. Okay, and this has happened mainly because of the fact that brain computation is learning oriented. As you give more and more data, okay, the parameters get fixed and the task gets done better. Okay, which is why we also say that it is important to it is important for the child to get exposed to as many experiences as possible. Okay, that fires the brain and sets the parameters for more enriching experience. That's why it is also important at the bachelor's level of education, not postgraduate. Okay, first year, second year, third year, one should be exposed to as many courses as possible. Okay, so that more and more data gets fed into the learning machine, which is our brain, and the parameters are set accordingly to deal with lots of new experiences, unforeseen experiences. Okay, so at the bachelor's level, one should have lots of exposure, a broad-based education. At the graduate level, you gradually specialize and go deeper into a topic. Now, the human brain is really the seat of consciousness and cognition, perhaps the most complex information processing machine in nature. Now, this was not the case. Interestingly, this was not the case for a long time. For a long time, it was thought that the seat of consciousness was in the heart, here. Okay, so this heart-brain dichotomy was there for a long time. And gradually it became clear that consciousness and cognition, the seat of that is the brain. Now, the beginner's brain map. So this is a very top level view of the brain. Brain is extremely, immensely complex, unimaginably complex. So brain has what is called the forebrain. This is called the cerebral cortex. It deals with language, mathematics, sensation, movement, cognition, emotion, and so on. Midbrain is the information routing area, and it has involuntary controls. Cerebellum is for motor control. Our limb movements are controlled by this area. Hindbrain deals with the control of breathing, heartbeat, blood circulation. Absolutely vital operations for survival. And spinal cord carries the reflexes, the information highway between the body and the brain. Okay. So these things are not known. I don't know if you've heard of a phrase called brain-gut axis. Okay, so there is a direct connection between the brain and our digestive system, or direct connection between the nervous system and the digestive system. That's why they affect each other. When we are anxious, afraid, angry, and so on, these emotions interfere with our digestive operations. Okay, so this is called the brain-gut axis. So the brain has these roughly big divisions: forebrain, midbrain, cerebellum, hindbrain, spinal cord. And the forebrain is what makes human beings humans. Okay, so fine arts, for example, mathematics, music, these are the functioning of the forebrain. Now, brain as a computational machine, we have seen all these differences before, and there are more elements. Brain is evolutionary. Brain has developed algorithms more suitable for survival over a very long period of time. The algorithms are still unknown, but the search is on. Brain is astonishing at the amount of information it processes. Typical computers 10 to the power 9 operations per second. Housefly brain 10 to the power 11 operations per second. Okay. And now there is also a comparison of large language models and brain. Okay, the large language models, the amount of power requirement in large language models is 100,000 times more than what is required in the brain. Okay. The amount of carbon footprint, that is the polluting influence on the environment, is again many times more than the brain. Human beings exhale carbon dioxide, right? And similarly, the power requirement, the energy requirement of the large language models also pollute the environment. So these large language models are extremely energy hungry and also pollute the environment quite a lot, much more than what the brain does or human beings do. So the brain facts and figures, basic building blocks of nervous system are nerve cells. We'll go into nerve cell and their computational model very soon. 10 to the power 12 neurons in the brain and 10 to the power 15 connections between them. Connections are made at the synapse, the speed, events on millisecond scale in neurons, nanosecond scale in silicon chips. Okay, average computers. And see this slowness in the brain, millisecond scale. But we are extremely proficient and fast in recognizing patterns. Another important point about the brain is Maslow's hierarchy. Maybe you have read about it in some course on psychology. So Maslow's hierarchy is a pyramidal structure where as living entities, our first instinct is survival. Okay? We must survive. The next requirement is food, rest, etc. Okay. Then the next requirement is achievement, recognition, and so on. And at the highest level of the Maslow's hierarchy, there are very few of this kind who like to contribute to humanity. Why is it a pyramidal structure? Because there are very few in this region. Very, very few. Okay, all the great men, maybe Jesus, Buddha, and so on. There are lots of entities at the bottom of the pyramid. Okay, if survival doesn't happen, the whole structure falls. Okay. So here the presence is not felt. Okay, the fact that I get food every day. Okay, I don't think about it. Okay, so its presence is not felt, but absence is critically felt. If food is not available, it hurts me very badly. But here, the presence is felt, absence is not felt by many. Okay, many probably don't care whether they're contributing to humanity or not. Okay, so this is an important point to remember. Absence is critically felt, presence is not felt. Here, presence is very impactfully felt, but absence is not missed. Okay, that is how the structure, arrangement of things are. This is called Maslow's hierarchy, and it directly corresponds to the structure of the brain. Okay, the higher brain is at operation when we are at a higher level of Maslow's hierarchy. These are some foundational points important for AI. Okay. Now let's move forward. The brain also has been mapped. Okay, so back of the brain, for example, is used for visual processing. It has been proved. The side areas of the brain are for auditory information processing. The sound that we hear, we process it. And there is a lot of resilience. Visual and auditory areas can do each other's job. If there is any damage in the visual processing area, then the two sides of the brain can take up that activity. Okay. Then this was the Nobel Prize winning work that the brain has two compartments, left brain and right brain. And for a right-handed person, the left brain deals with logic and the right brain deals with emotion, for example. Okay, the right brain is more holistic. The left brain is detail-oriented. So left brain is logic, reasoning, and verbal ability. Right brain is emotion and creativity. For example, in music, the left brain deals with words and right brain deals with the tune. Okay, and very interestingly, the limbs are also mapped to the brain. Okay, this finger, for example, this forefinger has a mapping in the brain. There is one particular part of the brain which is mapped to this finger. Okay, so all these have been very painstakingly, okay, over several decades, have been found by very painstaking research. Okay. Now the classical neuron has what is called the cell body, which is the most important part of the neuron. There are dendrites, which are receiving stations for the neurons. They receive the signals, and axon sends out the signals for two other neurons. Okay, so in the brain, there is continuous receiving and sending of signals at every neuron, and that is what leads to the recognition of patterns, language, vision, sound, and so on. So the computation in neurons happens in the following way. The signals come from other neurons, and there is a biological inner product which happens. Okay, for every neuron, there is a signal vector, and that is multiplied with the corresponding weights to the neuron, and sum is taken. This is called the biological inner product. It's a dot product. But this very simple view of neurons have been superseded by what is called a pyramidal structure of neurons. So we need not go into that. So what we'll do now is we'll take the building block of neural AI, okay, connectionist AI, the perceptron model. very simple computing device. This is the schematic of the perceptron. So the perceptron gives out an output Y for a threshold theta, and the inputs are x1, x2 up to xn. The weight values are w1 up w2 up to wn. Okay, this is the weight vector, the strengths of the connection, and this is the input vector. Now, what is the computation law for the perceptron? Y is equal to 1 if sigma wyxi is greater than or equal to theta, otherwise it is 0. Okay, so if we plot wyxi with y versus wyxi, then at theta the output shoots up to 1, and otherwise the output is 0. Okay, this is what the perceptron does. Now you can immediately see that a perceptron is by nature a classification device. For some vectors x, this if the summation is more than theta, then those vectors will be put in the class 1. Otherwise, the vector is in the class 0. What is the practical situation for this? Let's say a loan application has been given to a bank, or a visa application has been given to the embassy. And we have to decide if this application can be given visa or not. So it's a classification question. Okay, visa granted or not granted. So I represent the visa application by means of a vector where the components of the vector are income of the person, okay, a previous travel history, education, and so on. This gives me a vector, and the learning machine is this perceptron, let's say, whose parameters are the W1, W2 up to Wn. Now, W1, W2 up to Wn has been learned in such a way that a visa eligible application will give an output of 1, and an ineligible application will give an output of 0. Okay. Before that, we have to show to this perceptron lots of such vectors. For this vector, output 0. For this vector, output is 1. We have to give lots of data and train the machine. So the training will set the parameter values W1, W2 up to Wn. And then this machine will be able to decide visa granted or not granted. Okay. Of course, a single perceptron will not be able to do the job. We'll need many neurons connected together to do this job. But this is the basic idea. And in the human brain also, we continuously do classification. Okay, we identify if the person is angry or not. We identify if the coming object in front of me is dangerous or not. Is it a dog or cow? Now, those kind of decision making happens all the time. And the learning machine has been trained to do this. We are also born with a lot of innate abilities. The parameters are already preset because of genetics, hereditary influences, and so on. But environment gradually changes these parameters. And then we become fit for survival, fit for recognition, achievement, etc., etc. Okay, so we'll take this up. We'll go into the details of perceptron as an AI machine. Okay, this is another pillar of AI. So A star done. Now we are in perceptron. Then we'll go to logic. Okay, we'll cover all the important pillars first.